Lecture 25, Virtual Memory, Part 2. So we're going to continue on the discussion of virtual memory. We're just going to look at a few more advanced considerations to close out the topic, because it is a complicated endeavor, and there are some things that are worth talking about that we haven't really touched upon just yet. Okay, the first major new consideration is allocation of frames. In a simple system where we're not doing anything fancy, if there are n frames in the system, then we just use demand paging for all of them. So the initial state is that all frames are empty, and as needed, pages are read into those frames. Once pages have been read into all those frames, so all n are full, page n plus 1 needs to replace a page that's already in a frame because, well, there's no more space, right? We have to take something out of the frames to make room for the new thing. And when a process terminates, we could mark all the frames that it takes up as free. And that's perfectly easy. Nothing to do there. We don't have to evict them. They'll just get overwritten because they're marked as free. And in theory, one process could fill all the frames in the system. You know, evil, all mine, raccoon aside. There is a possibility that like one process is, if you will, if not monopolizing the resource, then like using an excessive amount of the resource of available frames. So that's the simplest approach where we didn't consider anything fancy. Now let's think about how can we build on that. All right, maybe you have some ideas, but I'll suggest at least kind of a first one, which is make a reservation. And we might reserve a few pages to be free at all times for performance reasons. As Jerry Seinfeld says, you know how to take the reservation, you just don't know how to hold the reservation, and that's kind of the important part. And if you don't recognize this is from the show Seinfeld, this is some OK Boomer stuff. Even I didn't really watch Seinfeld. Some of my parents liked. But yeah, moving on. The idea behind the reservation, right, is this idea that when we need to move something into a frame, if there are currently no frames available, we're going to have to evict something. We're going to have to choose what we're going to kick out and potentially write that out to disk, depending on whether it's been modified, whether we need to or not. So that potentially slows down the read, right? If we have to do a write first, we enqueue the write, we wait for the write to complete, then we schedule the read. The read takes place, and then we have the data. Whereas if we keep at least some frame free, we can always do the read into one of the free frames, and then we'll go through the process of deciding what we're going to kick out to restore sort of our minimum amount of free frames. And when we do that, the read doesn't have to wait for the write. The write can take place asynchronously, at a later time, when it's convenient for us to do that. And that maybe speeds up the performance of the program that wants to access the new page that we've just brought in. Right? So read not having to wait for the write does allow the user process to continue sooner than it otherwise would. Now, assuming, as we did talk about a little bit at least with cache, there might be some desire to allocate different numbers of frames to different processes, and maybe not necessarily let one very memory intensive process run wild and dominate all of memory. It's a choice. There are going to be pros and cons of each of those things, right? First one is we are constrained in the number of pages in actual memory, the number of frames that can actually be allocated to a given process. There's kind of no escaping the fact that memory only holds so much, and if memory is full, we can't put anything more. So the maximum number of frames a process can have is the maximum number of frames in the system. Alternatively, buy more RAM, assuming you have the kind of computer where you could actually add more RAM, which, as I say, isn't always a given anymore. Now, the minimum number is actually what's interesting here, right? Why do we care about the minimum? Well, the motivation behind a minimum number of frames is ostensibly performance. As long as our page replacement algorithm is sane, so not first in, first out, or not random, adding more frames will reduce the page fault rate for the program, and that will improve the performance of said program. And we haven't talked about scheduling yet. We're about to. But one of the goals of scheduling, as you may imagine, is like some measure of fairness, right? This idea that we don't want a process to never get a chance, or to have a completely miserable experience at the benefit of another process. So based on that, we might actually choose to allocate a minimum number of frames to each process to make sure that there's at least a baseline level of fairness. But what's the absolute minimum? And the answer is, well, actually, it's determined by the architecture. Not as in like house architecture. This would definitely, as shown here, never pass any kind of safety inspection. This is, quite frankly, horrifying from a safety point of view. I mean, I'm sure it looks cool, but you would not want to live there. Okay, but actually, as you know, I actually mean system architecture and not, house architecture. So imagine a machine where a memory reference instruction may contain one memory address. Load data from here to there, right? Like a copy instruction. In the worst case, then the instruction and the address are on different pages, so the instruction and the data that we need require 2 frames to be able to complete this instruction, right? We're going to move this data into a register, and that takes 2 pages, 2 frames, because the instruction is in the instructions and the data is allocated somewhere in the heap. Great. If the max frames for this process were 1, this instruction could never be completed, right? Why could it never be completed? Well, you see, when we load the instruction, we will find out, okay, we have a page fault where we need to fetch the data, and we put it in memory, but because this process is allowed only 1 page in memory at a time, we replace the page with the instruction. So when we try to restart the instruction and do it again, we have a page fault. So we go and fetch the instruction, and it replaces the page where the data was, and you can see why this wasn't going to work. Different architectures have different things. I mean, this is ancient history for sure, but like the IBM 370 had an MVC instruction, which moves data from one storage location to another. And the instruction itself is 6 bytes, and it's possible that the instruction straddles a page boundary just because of good or bad luck, depending on how you want to think about it. And so it could potentially require 6 frames for the source and the destination if they also straddle page boundaries. And there's also, in the architecture, an execute instruction, and the execute instruction is a way of saying, like, go here and do something. And if the execute instruction is also straddling a page boundary, it requires 2 more. So 8 frames potentially are needed. Is that super likely? No, but it just gives you an idea that the actual architecture is the determining factor for what is the minimum number of frames that a process can get away with if it's going to successfully execute all of its instructions. The problem could be actually infinitely bad if the architecture allows referencing of an indirect address. The address being referenced could be on another page, and that instruction itself could then reference another indirect address, and you can see how it's recursive at this point. Turtles all the way down, as the saying goes, that we could have an infinite chain, basically, of indirect references, or at least, if not an infinite one, then an arbitrary length chain. And an arbitrary length chain is a problem because then we need an arbitrary length number of pages to fill it all in. And as you can imagine, things could get a little painful. Dormammu, I've come to bargain, feeling like we've been here before, because we have. Okay, so in that case, right, the entire virtual memory has to be in main memory, which is generally speaking not possible. So we have to bargain. And the standard solution is to limit the levels of indirection to some value. If you can only have a chain that is 16 levels of indirection long, then the worst case scenario is a requirement of 17 pages. It's not a ridiculous amount. So how many levels of indirection do you actually need? This is a matter of taste. As long as you pick something and stick to it, we can actually answer the question of how many frames, how many pages need to be in those frames to execute an arbitrary program given our architecture. Right, rather like recursion leading to a stack overflow, it's possible that it prevents a program from running, but if it's in an infinite loop, we just terminate it. Okay, now assuming we don't just allocate every process the minimum or the maximum number of frames, right, there are some allocation algorithms that we could follow. We already kind of got a glimpse at this when we talked about, say, local versus global cache replacement. And if there are m frames in the system and the operating system reserves k of them for its own use, which is to say for the kernel, but also for things like having free pages, as we discussed a little bit earlier on, then there are m minus k frames available for processes. So option one is equal allocation. If there are n processes, then we say each process gets m minus k divided by n frames, and if the division produces a remainder, use those leftover frames as the pool of free frames for performance purposes, as we've discussed. So it sounds very fair. Everybody gets one slice of cake and one bottle of pop. But is it optimal? I mean, I don't know, right? Why does a text editing program get the same amount of frames as the web browser? Notepad and Chrome have vastly different memory needs. And why do they all get the same amount as a game, which tends to be very demanding on memory, right? You want to play Cyberpunk 2077 or something, you're not going to get away with just a text editor amount of frames to make that work. Next idea. Proportional allocation, which is each process should get a share of the frames according to its needs. So let the virtual memory size of a process P sub I be defined as S sub I, and therefore capital S is the sum of all of those virtual memory sizes. If the total number of frames is M and the operating system has K, we allocate A sub I frames to a process based on the formula below. A sub I is equal to S sub I divided by S times M minus K. That is to say, the number of allocated frames is basically the percentage of the total memory demands that the current process wants multiplied by the number of frames available. So if this process, its total wishes are 60% of memory, then it can get 60% of the frames. Now listen, the value of AI is only an estimate. Things may not divide evenly, which is obviously going to be a problem. So rounding is required, and minimums need to be enforced as well, based, as we've discussed just a minute ago, on the architecture of the system. And so to make that work, the sum of all the values cannot exceed the total available frames. So some of the larger processes will tend to have their allocations nudged down to make sure that smaller processes are brought up to the minimum. And typically we're going to round up in some of those scenarios as well. So if it's a large process, and although in principle it might be entitled to, let's say, 57% of the available frames, we might nudge it down so it's only like 56.8% of available frames, because we needed to hand over a few to make sure that smaller processes have the minimum. Thing is that with proportional allocation, as with equal allocation, there's no regard given to the priorities of the processes. And one of the ways that we could actually give priority to a process is to help it to execute faster, and the way that we would help it execute faster would be by giving it more frames, right? That would reduce its number of page faults and accordingly reduce the amount of time it spent waiting for data to be brought in to memory, and all of that sounds like it runs faster, right? Okay. So yeah, we haven't really talked a lot about priority, and I keep hinting that we're going to talk about scheduling and it's important, and you might even be thinking that it's actually like poor scheduling to put scheduling this far at the end of the course, but yeah, this is how things are. So priority matters a lot in scheduling. We will definitely be visiting that topic for an extended period soon. But let's just finish what we're doing with the virtual memory topic first. Okay, and think global, act local. I don't know, things raining down from the North Pole. I have questions. We've already discussed the idea of local and global replacement when we talked about caching, but you can have kind of a similar idea in main memory. So if we chose the least recently used algorithm in a global replacement policy, it's the least recently used page anywhere in memory that's replaced. If we chose the local policy, it's the least recently used page that belongs to the current process. Local is not really affected very much by our allocation concerns. So if we've said, all right, you get a fixed number of frames, or at least a specified number of frames, well then local replacement doesn't change very much because we just move things around as we need inside those allocated frames. But if we choose global allocation, then we'll see that there's a bit more of a dynamic aspect to it, right? The number of frames allocated to each process will change over time. And over time, global replacement algorithm means processes that run more often will accumulate more pages in memory, because when they're running, they are taking pages from somewhere, whether they were free or from somewhere else. And so it is very likely in this scenario that they end up taking more than are taken from them, meaning these processes end up with more stuff in memory overall. With that said, it probably makes sense from the point of view of the operating system to keep an eye on things, right? Watch how many frames a process has. It may be desirable to prevent a particular process from falling below a minimum threshold. And your minimum threshold doesn't have to be the absolute minimum as specified by the architecture, but it might just be like, okay, below this point, there would be so many page faults, it would actually be incredibly frustrating. So maybe it's for the best if we just swap that process out. Swap completely to disk a process that no longer meets the threshold. It's just not important enough right now. Let's leave it be, and we will come back to it another time. Speaking of things to come back to another time, I've mentioned already the idea of thrashing. And now it's time actually to return to that subject and make sure that we don't leave it forgotten. So in the introduction to virtual memory, I mentioned it, and the quick definition still applies, right? The operating system is spending so much time moving stuff into and out of memory that no useful work gets done. Aside from intentionally depriving the system of RAM, how do we get into this state? But perhaps more importantly, how do we get out of it? Okay, so let's consider a very simple example involving, shall we say, ancient operating systems. And in those ancient operating systems, you couldn't run everything all at the same time. It just didn't work very well. And so the operating system had built into it some logic that controlled how many processes could run at a time, and it would look at the CPU utilization and only the CPU utilization. If utilization is low, it means the CPU needs more work to do, which is to say start something or swap something into memory, get it going again, unsuspend a process. Okay. Global page replacement is used in this situation. So when a process gets a page fault, it just takes a frame from another process, and under most circumstances, this works just fine. Right? When we start new things, we're giving the CPU more work to do, and if in fact it is because the CPU is bored, well, then great, problem solved. The situation, however, can run until one process ends up getting a lot of page faults, like in a short period of time. And this is not unreasonable, right? If we think about how a typical program works, it could do the same thing all the time, or it could have different stages, right? The compiler is actually a really nice example of something that has like different stages. It has different phases to transform your code from what you typed in human readable language to the binary executable, right? There's reading the files, and there's parsing it, and then there's analyzing it, and there's generation of binary code, and those things are all different stages of the process, and they require like different functionality. And so, like, if the compiler has finished reading and parsing the input files, it's now going to do the analysis and the generation of binary code. That requires a whole bunch of new instruction pages, right? Because we're now doing completely different functionality, and a whole bunch of output space, right? Here's where we're going to put the results of the intermediate stages before we end up putting it all out to the binary file on disk. And so this is an opportunity to examine a situation where, we actually changed what the program is doing pretty radically. And when the process moves from one phase to another, right, it's going to have page faults, and those page faults result in taking pages from another process. And so this can happen if we've ended up loading in a lot of pages into those frames for the compiler. The other processes, the ones that just lost pages in frames to the compiler, well, they needed those, right? So when they get a turn to run, they are also going to generate a bunch of page faults because they needed whatever page was swapped out to continue executing. And so when this happens, we end up with sort of more and more requests that are queued for memory reads and writes, because we have all these pages that are needed, and we have all these I/O requests that are outstanding, so that we can continue working. But the fatal mistake is that the system, seeing that the CPU is not very busy because virtually all the processes are blocked for I/O, decides that we should schedule more programs to run. That makes it worse. A new process getting started, it needs at least the minimum number of pages. Those have to come from somewhere, so they will necessarily come from frames that are currently belonging to other processes, and this causes more page faults, more time spent paging, lower CPU utilization, and that triggers the operating system to start more processes. No work is getting done now, because, well, the operating system is spending all of its time moving pages into and out of memory, and this is thrashing, right? And this little diagram, I mean, it's cute, and conveniently there are no numbers associated with it, because that would be too easy, but it's just sort of to give you an idea of the progression of the curve, right? Like, starting more processes does increase CPU utilization up to a point, but at some point it results in thrashing because we are just moving stuff in and out of memory all the time. So we're not actually getting useful work done, right? The bureaucracy is expanding to meet the needs of the expanding bureaucracy. Okay, so what do we do if we suspect that thrashing is occurring? Yeah, we have to do the opposite. We have to actually decrease the number of processes that are in memory at a given time, right? If the problem is we're spending too much time switching between the various processes, the best thing that we can do in this situation is have fewer processes to switch between. Is it magic? Is it perfect? It's not always going to be an instant cure, but it is helpful. The other thing, of course, is recognizing that CPU usage alone is not a sufficient indicator as to whether more or few processes need to be running right now. If CPU utilization is low, it matters why. And looking into why and making a good decision is much more important than just saying, oh, well, this one indicator, is down, so we better do something about it. Another reason that causes low CPU usage, for example, is deadlock. Right? It doesn't mean that there aren't enough programs. It means we have a different kind of problem, and we need to take action to solve that, if we are going to solve it, as opposed to just starting more things, which may themselves just get snared in the deadlock. So it's not always so straightforward. So what if we stop using the global replacement and instead use local? Would that prevent us from getting into thrashing. It limits some of the damage, right? If process P1 is thrashing and it's not really executing very much because we're doing so much work to load pages in and out of memory, well, it can't steal pages from P2, so we don't get a cascade. Process P1 is unhappy, they're having a bad time, but other processes are able to continue as per usual. But nevertheless, process P2 is still affected at least a little bit. If P1 is spending a lot of time paging to and from disk, any other process that wants to use the disk is going to have to spend more time waiting because the queue is longer. So there's very small but noticeable effects on other processes. It's not as though you can just completely avoid this altogether and say, yep, that's process P1's problem, right? If they're having a bad time, everybody's having a bad time to at least a small degree. So we could decide whether we need to start or suspend programs based not just on CPU usage, but on the number of page faults that occur in a given period of time. And that's just kind of a good indication that maybe we have too much going on, right? And this is probably relatable, right? If you are trying to do too many things at the same time, you're trying to do some work and listen to music, and somebody's talking in the next room, and all these things, and you feel like you're sort of constantly switching between all the things that are going on, and you never get to concentrate on anything, that's a hint, right? There's too many context switches, there's too many page faults, if you will, that mean a lot of time is being lost in that regard. And maybe on co-op you've discussed with employers or supervisors or others about this idea that one of the things that managers try to do is try to minimize the number of context switches that employees have to do because context switches are costly, right? There is effort required to switch between tasks and put one thing down and pick up the next thing, and so they try to minimize it, right? And in my own experience, as a manager, I try to schedule all the meetings to be next to each other, so you don't end up getting into some work and then I have to stop what I'm doing and attend a stupid meeting, and then try to get back into the work afterwards. It's just difficult. So if there are too many page faults, it indicates we have too much going on. But that's reactive, right? If we're looking and counting the number of page faults, we might say, okay, if the page fault rate is elevated at this rate for this period of time, that's an indication that something is wrong and we should do something about it. But it's reactive. For how long have we been suffering this situation versus, could we be proactive? Could we deal with it before thrashing has started? All right, well, tell me the future then. It's not that easy to identify when thrashing would start, but part of the problem is we don't know in advance how many pages a process is going to need and when they're going to need them, and so you can't really ask. There's no way to ask for this information or get sort of a reliable answer from some third-party source. So we're going to have to rely on educated guessing. And you might hate that, right? Let's experiment and find out is good, but it's not always a solution. I hope medical experiments are not done on the basis of let's try it out and see what happens. Similarly, I don't think NASA plays around with satellites in orbit like it's a simulation. Just because those things are very expensive and you can't just send up a replacement if you need. But for software, usually we can just make a simulation, or we can just make our best guess. And if we're right, we're right. If we're wrong, we're wrong. Hopefully, this isn't a life or death scenario. So what do we know about process memory accesses? So we've said that they tend to obey the principle of locality, both temporal and spatial, and I presented to you an argument that said, okay, imagine you're iterating over an array. We have a summation, so we have a sum variable, and we have an array that contains some number of elements, and I said this hopefully gives you a good understanding of the idea of both temporal and spatial locality. But I didn't really prove that it's true, did I? right? We can think of like different parts of the program as different localities, as if they were areas on a map. Localities can overlap sometimes. And if we're correct, then giving a process enough frames for its locality means that it can operate in its area without encountering too many page faults. Not to say there won't be any. Things will not always be perfect, but we have sort of enough for the moment. Okay. Now, the question that I ask is, does the principle of locality actually hold? We don't have to verify that for ourselves. There is a reference here which recognizes, okay, here's a graph showing the locality of memory accesses, and here's execution time going from left to right along the bottom. This is a rather sort of ancient paper, but it is nevertheless still valid. But it shows the locality of memory accesses, and there's page numbers, and each little dot represents a hit where we referenced something a read or write in those pages. Okay, what's our takeaway from this graph? Is temporal locality, is spatial locality real? I'm going to argue yes. We can see over time, the patterns that have emerged. If our assumptions did not hold at all, this graph would look like white noise, right? If accesses were completely random, there was no way to predict when or where a future memory access was going to take place. This graph would just look like nothing, right? Look at the static on the screen. Oh, did you take a picture of snow, right? Because it would just be random noise. We wouldn't have anything to work off of. So, takeaway from this, hopefully, is that yes, locality is real. So, given that locality is real, let's move on and let's focus on actually making use of it then. So, the potential solution, as we've kind of touched on a little bit, is this idea of a working set model. And we're going to say that the last n pages in memory represent the locale of the program, so to speak. And assuming that most memory accesses are local, and we have a good reason to believe this is the case, then the most recent n pages will be the ones that are used most frequently, at least in the immediate future. In textbook descriptions, the n in this case that represents this locale is frequently referred to as delta, the working set window. And pages that have been recently used are in the working set. If a page has not been accessed recently, it will drop out of the working set after delta time units since its last reference. So suppose the window is defined as being 10 accesses. Any page that was accessed in the last 10 requests is considered part of the working set. If the next 10 memory accesses are all in page K, then after those further accesses, the working set contains only page K. If a page has not been used recently, we expect it to drop out. And so based on this, the size of the working set will change. It can be anything from one page up to maximum of delta. It's really just a question of what is the program doing. If delta is set to be too small, the working set does not encompass the entire locale, so we end up going outside this pretty frequently. If it's too large, it covers multiple locales. There's too much stuff in there. We're maintaining things that we do not need. So underestimating the size is bad, because it means there's more page faults, but overestimating isn't any better because it potentially means that we are expecting too many processes to be running, and we might restrict the ability of processes to run based on that. If the working set of every process is summed up, we get the total number of frames that each process would like in quotation marks, to have. If the sum exceeds the sort of m minus k available frames available in the system, at least one process is going to be unhappy. That is to say, it doesn't have as many frames as it needs. Like unhappy workers who go on strike, unhappy processes start thrashing. Right? They want to run, but they don't have enough resources, and they do not behave in the way that we were expecting. So, what do we do? Once a value of delta is determined, the operating system can monitor the working set of each process and use that to figure out if the system is currently overloaded. If that's the case, there's too much demand and not enough frames available to meet it, well, then the operating system can choose to, well, suspend a selected process, and then that will prevent thrashing. If the system is underloaded, that is to say there are not as many requests for frames as there are available frames, then, well, we could start something else, right? This would work. The page fault rate does tend to vary over time with a particular process. At the beginning, there's a bunch of page faults while a particular process gets started up, and then it's established, if you will, in its first locale. Once that happens, the number of page faults will drop until it moves to the new next place, and then the process begins again, so to speak. This is like with the compiler. If the first step of this of the compilation process is reading and parsing, there'll be a bunch of page faults associated with that, and then the reading and parsing can take place without quite so many page faults until we're ready to go on to, say, analysis. And then at that point, the number of page faults increases again, and it will eventually settle down before we go on to the next part. The next part is code generation, and again, there'll be a bunch of page faults associated with that when we get started. It's pretty common for a lot of processes to follow that kind of pattern. So what we are expecting, if you will, is for the working set to look something like this, right? The page fault rate rises temporarily until we're sort of settled in the new locale, and then it drops off. It's not necessarily going to drop to zero because we might still need to reference new things or load data from somewhere. But overall, we do expect it to be a lot lower. Maybe this doesn't really sort of make sense. Let me try to explain with an analogy. Let's say that you have moved to a new city for a co-op term. Like you've never been to Ottawa before, and your next co-op is located there. Or should I say California? Sure. You've never been to Cupertino before. So you don't know where anything is in this place, right? So when you move, you frequently rely on Google Maps or whatever other map program you like, Apple Maps or anything, doesn't matter, until you know what you're looking for, right? So you want to find a supermarket. Well, you don't know where there is one, so you're going to have to search for it, right? You want to, I don't know, find a coffee shop, again, search for it. You're looking for a place to find, I don't know, Italian food, again, you search for it. So you ask Google, right? And once you've been there, you've sort of established a certain level of familiarity with the place, right? Once you know the way to the grocery store, it is part of your working set. And you don't have to ask Google again. I mean, you can, but when you go places frequently enough, you've sort of learned where they are, you remember how to get there. You don't have to check into it every single time, right? And you did the same thing at university. When you came to university, you probably didn't know off the cuff where any of the buildings were, but okay, now I know where's E5, where's STC, where's E7, where's PAC. Like all those things you learn and you add them to your working set, and when they're in your working set, you don't have to look it up every single time. And so this is fairly convenient, right? And you don't have to ask again. Now, I'm making the analogy here that, say, not knowing where the grocery store is like page fault. Asking Google is like asking the operating system to bring that page in from disk. Once it's done so, it stays in your working set, and you don't have to ask again. Assuming you remember where it is, which most likely you do, but you might have to ask more than once. We've all been there. Now, this works until your next co-op term. If your next co-op term is a different place, and you go to Seattle, again, you're going to have to relearn, if you will, everything and where it all is by, once again, asking Google to fill in the information for you, because you don't know where the supermarket is, you don't know where the coffee shop is, you don't know how to get to the office. All of those things are new. The the way that this analogy sort of falls down, right, is that like after your co-op term in California, you come back to Waterloo and you haven't completely forgotten everything you know about Waterloo. I mean, I hope you haven't. I mean, maybe you have, but presumably you haven't. So you don't have quite the same situation as as a program where all of the pages from Waterloo were swapped out, and you would have to swap them all in again. Like you still remember where to go get food to eat when you come back to Waterloo. Some places have probably changed, when you've been away for any meaningful period of time, but not enough so that like everything you know about it is useless, right? And for the computer, when you swapped out by going to a different locale, you've forgotten everything you know in main memory. So it's not quite as dramatic for us as it is for the CPU. Okay, that will conclude our discussion on main memory and virtual memory and how the operating system is responsible for managing it and various management schemes associated therewith. Our next topic, finally, is the one about scheduling, and I've been referencing it off and on basically the whole time, so now we're finally ready to get into it. So let's do it.